Hey, Paul.
Hey there, how you doing?
I'm doing good. So you're headed down the stretch of calculus, huh?
Yeah, we have our final this week, and then the AP test is next week.
Okay. Um, so this is a test you took already, or this was kind of like a practice test, or?
It was kind of like a practice test for what our final, and then also for studying for the AP exam. So I
Okay.
thought it might be helpful to go over some of the stuff I'm not
Yeah,
too sure on.
for sure. Now, these are your answers that are circled?
Yeah, some of them are right, some of them are wrong, but I was thinking we could just ignore them and just
Okay.
go over some of the problems, I guess.
Where do you want to start?
Um,
We got 17
start with
problems here. We might have time to go over all of them.
okay. We just start at the beginning, I guess.
Okay.
Make it easy.
The graph of the function f is shown above. For which of the following values of x is f prime of x positive and increasing? Well, we know that f prime of x, to be positive, has to have positive slopes. Okay, if we look at point A, that's got a negative slope, so that's not going to qualify. Point B is a cusp, so we don't even know what the slope is there. Point C has a positive slope, but notice that the slope is decreasing. Point D has a negative slope, so that doesn't count. Point E has a positive slope that is getting more positive as we move to the right. So it would be E. It's positive and it's increasing. In other words, if I were to graph the first derivative of this function, it would be 0 right there.
Mm.
And then because this function is increasing, the first derivative would be positive. And because this function is concave up, the first derivative is increasing. And
Right.
the second derivative would be positive. If the first derivative is increasing, the second derivative is positive. And a positive second derivative means it's concave up. And we can see that it is. Now, might be a little helpful if I show you this thing. I probably showed it to you before. And let's see where I store it. Maybe in the calculus. Hold on a second. No, don't store it in this calculus. I store it in this calculus. Have I shown you this before?
I think so, but it'd probably be good to go over it again.
It's helpful. This is the function. This is the first derivative. This is the second derivative. The key things are if the function is increasing, the first derivative's got to be in positive territory. You can see the first derivative is in positive territory. It's decreasing, but it's in positive territory. Okay? As the function hits a local maximum, first derivative is going to be 0. The slope of that is 0. As the function decreases, first derivative is in negative territory that whole way. As the function hits its local minimum, first derivative is 0 again. Then the function starts increasing and the first derivative is positive for all of that. Now, the same relationship holds from the first derivative to the function as from the second derivative to the first derivative. In other words, the second derivative is the first derivative of the first derivative. So I can say the same thing. If the first derivative is decreasing, second derivative has to be in negative territory, which it is. As the first derivative has a local minimum, second derivative has to be 0. Also, when the second derivative is 0, we're looking at a point of inception, or what's the word?
Inflection.
Inflection. It's been a while. I've been doing mainly Calc BC here lately.
Okay.
Yeah, but that's a point of inflection, which is the point where it goes from concave down to concave up. The point where concavity changes is a point of inflection. It's where the second derivative is always going to be 0. So let's look at these problems. Let me keep this available. And so this is the function, and f prime is the plot of all of these slopes. In other words, I can figure out what the slope is at point C. It's positive, but it's not increasing. At point D, the slope is negative. Only point E is it positive, and it's increasing because it's concave up. Concave up means it's going to be increasing, and the second derivative would be in positive territory. If the second derivative is in positive territory, then it's increasing. Okay?
Okay, that makes sense.
Okay, let's look at 77. The intermediate value theorem says that if f of 2 is equal to 10 and f of 4 is equal to 20, then it has to cover the values between 10 and 20 when it goes from 2 to 4 because it's continuous. In other words, there's no way it can jump over any value from 10 to 20. It's got to go through 11, 12, 13, every number. Otherwise, it wouldn't be continuous. So f of x has to equal 13 has at least one solution in that interval, and that is true.
Okay, and that's just basically all the intermediate value theorem states.
So all the intermediate value states is that if I have a function and I know that the value of the function here is 10, and the value of the function here is 20 on the y scale, I cannot get, if this function is continuous, I cannot get from there to there without going through all values between 10 and 20, no matter how I draw that function. In other words, I could draw the function this way. As long as it's continuous, then it has to have all of those values.
Okay. That makes sense.
And that's what the intermediate value says, is that there must be all of the intermediate values between 10 and 20. All right. Here, let me drop this down a little bit. Let's do this way. All right. Y equals e to the tan x minus 2. Crosses the x-axis at one point in the interval 0 to 1. What is the slope of the graph at that point? Well, I have no idea what this graph looks like. Let's see. Probably something like tan of e to the x minus 2, so something like that. My guess. Where does it cross the x-axis? How do we determine where it crosses the x-axis?
Can we set it to equal to 0?
Yeah. So we're going to set y equal to 0, which is what happens when we're crossing the x-axis. I'm going to move the 2 to the other side and solve this equation.
So we have to use the natural log to get rid of the e?
Yeah. So we got natural log of 2 equals natural log of that. And then the natural log of e to the tan x just is tan x. Because the natural, in other words, I can take that tan x and put it in front. And then the natural log of e is 1. So I've got tan x equals log 2. So x would be what?
Not too sure where to take it from there.
I have to take the inverse tan of both sides.
Oh, yeah.
I'm going to take the inverse tan of this side. I'm going to take the inverse tan of that side. The inverse tan of tan x is just x. So the answer is the inverse tan of natural log 2. Do you have your calculator in front of you?
I do. That equals 0.606.
Okay. Which is okay, they want the slope of the graph at that point.
Mm-hmm.
Well, let's find the slope of this graph and then plug in this point for x to find out what the slope is. Well, the slope of this graph is y prime. So I want to solve for y prime, and then I want to evaluate y prime at 0.606 because that's where it crosses the x-axis, and that would give me the slope at that point. So what is y prime, first of all?
So we'd have to take the derivative of the first function.
Okay, use the chain rule.
So the derivative of e to the, it'd be e to the u, and wouldn't that just be e to the u?
Right, e to the tan x, but then we need to multiply it by the derivative of the inside.
Mm-hmm.
In other words, the derivative of e to the u, excuse me, been doing too much integration lately, the derivative of e to the u is equal to e to the u times du dx, which is the derivative of the inside. So it's e to the tan x times the derivative of tan x, which is what?
Isn't that secant squared x?
Okay. So there's our slope at any point along the x-axis. So let's plug in 6.06. So the slope at 0.606 is going to be e to the tan of 0.606 times the secant squared of 0.606. Do that in your calculator
All right.
if you can. We might actually, go ahead, what answer did you get?
Okay, 2.432.
2.432.
Yeah. I don't know, I'm looking to see if I'm, oh, I did not square it. That might be the problem.
Okay. So we just need to take that 2.42 and multiply it by secant of 0.606.
For some reason, I'm not getting any of these answers.
Well, what do you get? Because it indicated that you might have to take the closest one. So the first answer you came up with was 2.4. And if we multiply that by the secant of 0.606, we'll solve the problem that you didn't square it. What's the secant of 0.606? Make sure you're in radians.
Right. It's 1.21.
Aha. Okay. So we multiply 1.21 times 2.4, and I bet we get 2.96.
Yep,
Something very close to that. Okay. So we don't know whether you got these right or wrong.
No, I didn't mark those down.
That's all right. Doesn't really matter. Doesn't really matter.
These particle problems seem to be pretty common in our tests.
Yeah, they are. They're definitely, everybody loves them. Okay, the velocity at time t is given by that v of t. Acceleration is given by a of t, which gives the following, or which of the following gives the average velocity? Well, we know that the average of any function is the integral of that function evaluated from 0 to 8 divided by 1 over b minus a, which is that. So it's 1 over 8 times the integral from 0 to 8 of the velocity function dt.
So it ended up being answered.
Or it's b. I just realized that b is the same thing. So the question is it the absolute value? And the answer is no. The answer is b, not c.
Okay.
And the reason is that if you have this particle moving on a line, here's the 0 point, and the particle goes like this to the right, and then goes like that to the left, and then goes like that to the right, the average velocity is going to be very close to 0 because we got some positive velocities, we got some negative velocities. So it's not the integral of the absolute value. It's the integral. If you look in the book under the average, it doesn't say absolute value for that. Boy, I don't even know where that is. Do you know what page that function is defined on?
I do not.
Yeah, I've read this book so many times that I don't remember precisely where that is the average is defined. But I don't want to waste all the time looking it up either. Here. Average, no. That's in the next chapter. Yeah. One second. Yeah, here we go. It's in the section on integrals. And it is on page 271 of the book. The average mean value of a function is 1 over b minus a times the integral from a to b of f of x dx, not the absolute value of f of x.
Okay.
Okay. All right. graph of f prime, the derivative of f is shown here, not f. This is f prime. Which of the following statements must be true? F has the original function has a relative minimum at x equal minus 3, right there. Is that true or false?
That point would either be a maximum or a minimum, but it's I think it's a maximum.
Okay.
Or no.
If it's a minimum, in other words, if it looks like that, where there are relative minimums, what happens to the slope? The slope goes from negative, 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 0 to positive, 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 positive. So that's what we're looking for. Well, what's happening here? The slope is going goes from negative to positive on the other side of that 0 point. That's what we need it to do. We need the slopes to go from negative to positive for it to be a relative minimum. If the slopes are going from positive to negative, then it's going to be a relative maximum. See the difference?
Yeah.
By looking at what the slopes do prior and afterwards, we can tell that that point, in other words, our two potential minimums and maximums are here and here, if you can see that, at minus 3 and plus 2, because that's where the first derivative is 0. We just don't know if it's 0 because it's the bottom of a minimum or it's 0 because it's the top of a maximum. However, by analyzing the fact that the slope is negative here, positive there, it's this model right there. So 1 is true. It does have a relative minimum at x equal minus 3. The graph of f has a point of inflection at x equal minus 2. Right here. Well, what do we know about points of inflection is that the second derivative is 0.
So that wouldn't be an inflection point then?
It's kind of hard to tell whether that's a 0 slope or not. In other words, remember this is the first derivative graph. So this is the graph of the slopes of the original function. Now, I can't tell if that has a slope of 0. Does that go like this? Or does it go like this? In other words, does it flatten out right here? It's hard to tell.
I would assume it does, but it is hard to tell.
There's certainly an inflection point there in the first derivative curve. In other words, we're going from concave down to concave up, and that's the point that kind of separates them. So if the original function looked like this, I would say, yes, that's an inflection point. But this appears to be an inflection point of the first derivative. And I don't think we can say that the function f has a point of inflection there. So I'm going to say no to 2. 3, the graph of f is concave down from 0 to 4, from here to here. Well, what do we know about concave down? Concave down is when the second derivative is negative. Right?
Mm-hmm.
When the second derivative is positive, it's concave up. When the second derivative is negative, it's concave down. what is the second derivative between this point and this point? Is it positive or negative? Or both?
It's both.
It's actually, remember that if a function is always decreasing, its first derivative has to be negative.
Mm-hmm.
This function is decreasing from 0 to 4. Since this is decreasing, I know that the second derivative is negative from 0 to 4. And if the second derivative is negative from 0 to 4, the original function is concave up. So 1 and 3.
Okay.
It's possible that 2, let me just notice on this original function, the point of inflection right there, if you can see my hand, corresponds with where the second derivative is 0. And there's only one point. And the second derivative has to be 0 for the original function to have an inflection point. Well, if we look at this, the second derivative is going to be the slopes of the first derivative. So the second derivative is clearly 0 right here, so there's an inflection point. But I can't say for sure whether we have a slope of 0 right there. And it doesn't really look like we do. It looks like it's more like this than it is like this. Just as an example, let's take the curve y equal x cubed. This is the original function, which if I plot it, plots like this. That is an inflection point. Because it's the difference between where it goes concave down to concave up. Now, the first derivative is 0 here. But so is the second derivative, because I know that's an inflection point. All right. I'm not sure what point I was going to make there, but pretty sure the answer is 1 and 3 on this.
Okay, that makes sense.
Yeah. Okay, this question is integral as net change. In other words, if you know a rate that water is being pumped into the tank, then I can integrate that rate function over the time 0 to 20, and that will be how much gallons of water is pumped into that tank in the first 20 minutes. So your answer here is correct. You're going to take the integral from 0 to 20 of that function, r of t, and since it started with 800, we're going to add 800 to it. In other words, it really should be written kind of like this. It's 800 plus the integral from 0 to 20 of r of t dt. So I presume this is probably one where they are going to allow you to use your calculator to come up with this answer?
Yeah, it is.
Okay. So I'm presuming you know how to put that in your calculator?
Yeah, I do.
Okay. If not, I have a program called Wolfram Alpha that I can put this same function in if we need to verify these. But rather than spend our time evaluating that, since you can do it on the computer, let's kind of spend our time figuring out how to set these up. Okay, f prime, this one gave me a little trouble, is equal f has a local maximum at x equal, well, if I'm going to use the first derivative test, I'm going to set that equal to 0 and solve for it. Now here's where the problem comes in. Can you do this on your calculator?
Yeah, I think most of these were calculator problems, I believe.
Okay. There is a function on your, you have a TI-84 or an Inspire?
I have a TI-84.
There's a problem-solving capability on that. Or you could just plot that function as a graph and figure out where it's equal to 0. And that's the answer. Because this isn't terribly easy to solve algebraically, notice.
Mm-hmm.
I would have to move these two terms to the other side. So I got minus x cubed plus 3x equals this. And then I'm going to have to square both sides. Squaring this side here is going to get really ugly. And I'll be left with x to the 4th plus 1 on the right. And I'll be left with like x to the 6th plus some x squareds. And then solving that for the zeros is going to be even tougher. So as long as you're allowed to use your calculator to solve for x, and you know how to do it, then that would be your answer. I guess
Okay.
We can always put in that number. In other words, we can almost back solve this. You know what I'm saying? If you didn't know how to solve this on your calculator, then you could back solve it. You could try each of these answers for x and see if it's equal to 0. Not that that would be terrifically easy to do, but we certainly could test as to whether that's the correct answer or not. Just plug it in for x and see if we get 0.
I think I can use the graph to figure it out.
Yeah, I think so also.
Yeah.
What were you doing here? Is that 1/2 x to the 4th plus 1 to the 1/2?
Yeah, I think I was trying to get the derivative, or I don't know exactly what I was doing.
This is the derivative. So,
Yeah.
and local maximums occur when the derivative is equal to 0. So it's all about solving this. Now, you will find multiple solutions because this is, after all, at least a cubic. So you're liable to find 3 solutions where it's equal to 0. And then you can either apply the second derivative test or the first derivative test as to whether or not it's a maximum or a minimum. Here's the first derivative test. Let's say we want to figure out where the local minimum and where the local maximum is. We're going to take the derivative. There's 2 places where the slope is 0, there and there. The first derivative test says that the slope has to be change sign from plus to minus for it to be a maximum. Notice that when the slope changes sign from negative to positive, it's a minimum. So there's the first derivative test. Second derivative test, if you want to use that, is it's a maximum if the second derivative is concave down or negative. It's a minimum if the second derivative is concave up or positive. So there's a first derivative test and there's a second derivative test.
Okay.
So what you would want to do is whatever answer your computer gives you, let's say it gives you 3 different answers. Well, we want to test a value slightly to the left of this. Make sure that we get a negative slope. Slightly to the right of that, make sure we get a positive slope, and that makes that a local maximum. In other words, we can apply the first derivative test here. We'll test the point. If we think this is the answer, then we would plug in 0.8 into this function, and hopefully you have a positive slope. If we plug in the 0.83 or 0.84, and we get a negative slope, that means it's a maximum because it went from positive slope to negative slope.
Right.
So that's how we, in other words, since there's liable to be 3 different values of x that show you that you have either a maximum or a minimum, then we're going to have to apply the first derivative test to determine whether that's the maximum there.
And then just to clarify, the positive, negative, that's increasing and decreasing for this, right? Or is it?
Well, it's actually, if we figure out what f prime is the slope.
Mm-hmm.
So if this is the correct answer, then immediately to the left of this value, we must have positive slopes. We know that at this value, we have a 0 slope.
Okay.
For it to be a maximum, we have to have positive slopes immediately to the left of this value and negative slopes immediately to the right. And we figure that up by plugging in a point immediately to the left, like 0.8, making sure that this f prime of x is a positive number, meaning it would have a positive slope at x equal 0.8. In other words, this point right here is 0.829. So to the left of 0.829, we need a positive slope. To the right of 0.829, we need a negative slope. So if I plug in 0.83, that should be a positive number. Excuse me, that should be a negative number. It's got to be negative to the right, positive to the left. If it's the reverse, then it's not a maximum, it's a minimum. Notice that if we have a minimum, it's negative prior, positive coming out.
Okay.
Okay?
I think I see what I did wrong there.
Okay. Well, I'm not sure that's not the right answer. It might be. But we probably need to apply that test. Because it wouldn't surprise me if x, you're going to have 3 values, because this is basically a cubic function. In other words, the square root of x to the 4th is x squared, essentially. So you have an x cubed, an x squared, and an x. Should have 3 solutions. Probably at least 2 of those solutions are listed here. So we need to check. Let's say we solve this and we get 2 different values. We get x equal 0.829 or x equal 1.234. Now, to determine which of those is a minimum and which of them is a maximum, I have to apply the first derivative test. And substitute points to the left and right of this and the left and right of this, and that will clarify the problem. And the first derivative test is a little easier than the second derivative test because taking the second derivative of that is a little tricky. It gets a little messy. So it's actually easier to plug in points left and right of this value and determine whether the slope is plus or minus left and right. All right. Okay, here we have a velocity function which is not given to us, only shown to us. And they want to know the distance traveled by the car. Well, this is integral as net change, which means that if I knew this function, I would integrate it from 0 to 8. But that's the same thing. In other words, the integral, the integral from 0 to 8 of v of t dt, which is going to be our answer, is the area under that curve, which we have another way of getting, and you've done that here, and just add up the squares. Each one of these is 10. So there's 50, 46, 40 approximately, and it looks like we get 210. Is that what you did?
Yeah, that is.
Just added everything up to the best approximation you can. In other words, this one's not really 20. It's a little less than 20.
Yeah.
This one's a little less than 10. So if you added up all of these numbers, you'd probably get something greater than 210. It's 90.
It also does under approximate it at the beginning of the function.
86, 196. It does underestimate it at the beginning and overestimates it at the end. Even still, it's a little tricky to do this. I'm surprised they give two answers here that are so close. Notice that we got 136, 166, 186, 196. So 196 is what we get when we use a right rectangle method, which underestimates it there, underestimates it there, underestimates it there, and overestimates it slightly there. But still, 196 is almost exactly halfway in between 180 and 210.
Yeah, I had a bit of trouble deciding between those as well.
Yeah, and I'm not sure how to decide that. Because it looks to me like this underestimation pretty much offsets this overestimation. I guess I would go with the 210. I would assume that it's more overestimated here than it is underestimated there. So I would round up the distance.
Mm-hmm.
All right. Concept is what's important there. Hopefully, if you get a problem on a test, it won't be ambiguous like that.
Yeah.
That's pretty ambiguous. They didn't need to put answers that close together. All right, 84. Let f be a function whose first derivative is given by that. Which of the following are all intervals on which the graph of f is concave down? Okay. We've decided that concave down means the second derivative is negative. Right? Yeah. When concave down, concavity. Concave up on any interval where y double prime is greater than 0. Concave down on any interval where y double prime is less than 0. That's the second derivative concavity test. So We're looking at the first derivative, so we need to take the second derivative of this and figure out whether it's which interval it's positive or negative. So let's first take the second derivative. And what is that going to be?
So that'd be e to the u times 4
There's e to the u.
Okay.
Times the derivative of u.
Mm-hmm. Which would be 4x cubed minus 4x.
So there's the second derivative. And we want to know on what intervals that is negative. So where is this function less than 0? We're going to set the second derivative less than 0, which would mean that the original function was concave down on that entire interval. Okay, let's see. How do we solve this? Well, this is always positive, correct?
Yeah.
When you take any positive number and take it to an exponent, it's positive. There's no way to make it negative. So if this is always positive, then we need 4x cubed minus 4x to be negative. Well, let's factor out a 4x times x squared minus 1 less than 0. And that is 4x times x plus 1 times x minus 1 less than 0. Do you remember how we solved these?
I don't.
The inequality, we need a sign chart. There's 0 on our sign chart. We also need the critical points because we're going to test to the left and right of all critical points, and that'll tell us whether it's plus or minus on that particular interval. So what are my 3 critical points here?
So it'd be 0, -1, and 1.
Okay. So let's test to the left of -1. When we do a -2, this is negative, this is negative, this is negative. 3 negatives equal a negative. So we're negative everywhere to the left of 2. And I could go all the way to infinity. I know it's negative. Because these 3 critical points, I only need to test 1 point to the left. Now let's test a point between 0 and -1. So let's try -1/2. -1/2, that's negative. -1/2, that's positive. -1/2, that's negative. The product of negative times negative is positive. Now let's test +1/2. That's positive, that's positive, that's negative. So it's negative, and now let's test a point to the right of 1, positive, positive, positive. Now what is our interval? Our interval is x less than -1 or x between greater than 0 and less than 1. Well, we only needed to look at the interval from negative 1.5 to 1.5. So that answer is D. In other words, from negative 1.5 to negative 1, this is 0, less than 0. And from 0 to 1, the second derivative is negative also.
All right.
The trickiest part about this problem was recognizing that this is always positive. Because then we can just solve this. It would be a difficult problem if I had to solve when this whole thing is less than 0. That's going to be very tricky. But since I know that this part of it has to be positive, then the only part that I'm looking to be negative is this part here. And I set that less than 0 and solve it. Okay?
Okay.
If I go on and you still have questions, stop me and we'll go back.
Okay.
Okay? I want to go on just until you understand it. Okay, the graph we're looking at is f prime, the derivative of f. The function f has a local maximum at x equal, what are the two possibilities?
It should be either 1 or negative 3.
Correct, because that's where the first derivative is equal to 0. Okay, which means the original function either looks like that or it looks like this at those 2 points. Well, let's apply the first derivative test. On the first derivative test, for this to be a maximum, we got to go in with positive slopes and come out with negative slopes. Well, you said here we went in positive slopes, coming out with negative slopes. So that is a local maximum right there. Notice that at negative 3, we go in with negative slopes. This also is a little tricky. When I say this slope is negative, you do see why that's negative, right?
Yeah.
Even though it's increasing. Increasing merely means that the second derivative is positive. But this means that the slope prior to minus 3 was negative because it's below the x-axis. That's why it's negative. And the slope after negative 3 is positive because it's above the x-axis. So this 0 point right here must be this situation. That's got to be a relative minimum. Okay?
Okay.
These problems. Calculus sure does find ways to ask these problems that are just kind of different than everything you do in calculus class.
Yeah.
It is. It's kind of amazing. You have to really get used to these kind of questions. They're tricky. Okay. If f prime of x is greater than 0 for all x, what does that mean? That means the original function is increasing for all x. In other words, if the original function is doing this, then the first derivative has to be positive between those 2 points because the original function is increasing, first derivative has to be positive. So by telling me the first derivative is positive, I know the original function is increasing. Let's see if that is what we need. And the integral of the original function is equal to 0 between 4 and 7. Which of the following could be a table of values for the function f? Notice that if the integral, if this was my original function, whoops, gosh, what in the world did I do? If this was my original function, notice that the area could not be 0, right? Between 4 and 7. In other words, this integral gives us the area under that curve. So what that means is that we must have some negative values there. That must be my x-axis. If the area from 4 to 7 is 0, some of it must be negative, some of it must be positive. So it has to have some negative values in it. If it was all positive values, there's no way the area under the curve could be 0. Okay? So, which of the following could be values? Well, let's think about this for a second. In other words, the picture that I've drawn here, that could be the -4 for A. At x equal 5, we could still be in negative territory. That could be -3. And then at 7, the function is 0. Well, could this be correct? Could that be 0 right there? Not if f prime of x is greater than 0, because the only way I can make it 0 at 7 is if this function turns around and comes back down like that. In other words, if we know the function is always increasing, right? So if it's negative here and it's negative there, -4, -3, and it's 0 there, then the area, and it has to always be increasing, so it has to be like this. Well, the area under that curve is going to be negative. So that can't be the right answer, because it has to always be increasing. This, B, could be the right answer. We have a -4 there. At 5, we have a -2. And at 7, we are above the y-axis. So it's possible that if we integrate from 4 to 7, this negative area perfectly balances out this positive area, and that integral is going to be equal to 0. So B could be right. Which of the following could be a table of values? Well, B could be right, but notice that C cannot. Do you see why C cannot be right?
Because it's not always increasing.
Exactly. It starts negative, goes up to 6, and then goes down to 3. So it's falling from 5 to 7. And D, that's not always increasing. That is flat between 4 and 7. So between 4 and 7, that function is going to either have to be a straight line, which would give you an area of 0. But if it's anything other than a straight line, it can't always decrease. In other words, it would have to decrease to have all of those values at 0. So it wouldn't work. So B is the only thing that is possible. And you've drawn a pretty good picture of it here.
Thank you.
Yeah. And here, in fact. In other words, this one shows you that that area would have to be negative, not 0. All right. Oh, I didn't look at E. But notice E goes 0, 4, 6, which is above the x-axis the whole way. If it's always increasing, that's going to be a positive area.
Mm-hmm.
Okay. Now here we have the second derivative. What are the intervals on which the function is concave down? Well, that's pretty straightforward. Do you remember what the second derivative has to be for it to
Does
be?
it have to be? Does it have to be negative, or is it?
Yes. Yes.
Okay.
So we're looking for where on this second derivative graph it's negative. Well, clearly to the left of -1 it's negative. That means the original function is concave down. It's concave down here. It's concave down there. So certainly between 1 and 3 it's concave down. And when x is less than -1, it's concave down. So it's answer E. X being between -1 and -2, which is what that says, or x is between 1 and 3, which is the second part of it.
Okay.
So is this person being hanged by a light pole? No.
I drew that line in
I
there.
suspect not, yeah. It does look like that, doesn't it? Okay, so a person whose height is 6 feet is walking away from the base of a street light along a straight path at a rate of 4 feet per second. The height of the street light's 15 feet. What is the rate of the person's shadow? This is a great problem, the shadow problem. Notice that the shadow is going to move faster than the person, right? As this person gets further and further away, his shadow gets longer and longer. So the only way that can happen is if the shadow is moving faster than the person is. This part of the shadow has to actually move faster than the person for it to, because by the time the person's way out here, that shadow is going to be a lot longer because the angle is different.
Right.
Okay, so this is a related rate problem. There's our 6-foot person. There's our 15-foot light. And we'll call X what is the rate at which the person's shadow is lengthening? Well, that would be dx dt, right?
Mm-hmm.
In other words, that's what they're asking for, is dx dt from my diagram. Dx dt would be the change in the rate of x. Right now, x is the measurement from the light pole to the end of the shadow. Well, if we want to know, as this person walks to the right, what the end of the shadow does is it goes to there now. Okay, so we have a right triangle here. So if we set up the equation for the right triangle, the hypotenuse, which we'll call z, z squared equals 15 squared plus x squared. All right, let's see. What are they giving us? They're giving us the rate that the person is moving. Let's have two variables here.
Okay.
Let's have x and let's have y. X being for the moment, let's use two variables. In which case, they've given us dx dt is 4 feet per second. That's how fast the person's moving.
Mm-hmm.
And we want to calculate dy dt. So we need an equation that relates everything together. Then we need to implicitly differentiate it and plug in the knowns and what we're trying to figure out. Dy dt is what we're looking for, because that would be the rate of his shadow moving.
Mm-hmm.
So I've got 15 squared plus y squared equals z squared. That doesn't do me much good. These are also similar triangles. So I can say 15 is to 6 as y minus x as y is to y minus x. In other words, this dimension right here is y minus x. Okay, that's a true statement, and that's going to get it done. Okay, you see where I got this equation from?
Yeah.
We got two similar triangles. 15 is to this side 6 as the full bottom side. Y is to this dimension here, which is y minus x. So now, if I differentiate this, let's take away my picture for a moment. Let's see, I've got 15y minus 15x equals 6y. Well, let's simplify that. That's 9y minus 15x equals 0. Now let's differentiate it with respect to t implicitly. So this is going to be y times dy dt minus 15 times dx dt equals 0. We're trying to solve for dy dt, and we were given that dx dt is equal to 4. So let's see if that works. So we've got dy dt is equal to, if I plug in 4 for that, I get 60 on the other side divided by 9. That should be the answer, 6.7. Whoops, I'm looking at the wrong problem. 6. I think I actually did it right. I don't think I've omitted anything. This sounds, that's not going to be correct for sure.
Yeah.
Because one thing we know for absolute certain is that it's got to be greater than 4. Right? There's no way the shadow can move slower than the person, because the shadow is lengthening as the person moves. So if the shadow is lengthening, the back of the shadow might be moving at 4 feet per second, but the front of the shadow has to be moving faster than that. So I'm pretty sure this is correct, and this gives us an answer of approximately 6.5 D. Not quite sure why they're off so much, because there was nothing complicated in any of this. The precise answer is 60 divided by 9, which is more like 6 2/3. But given their comment at the beginning of the test, where pick the closest one, I'd have to go with that. And it doesn't seem like the shadow should be moving 2.5 times as fast as the person.
Yeah.
So that answer makes more sense than this does also. All right. Oh, wow. I've totally lost track of time here, Paul.
Sorry about that.
That's okay. It's my fault, not yours. When I get into calculus, I really get into it, and I don't see anything else going on around me. Let's see. We're on 89. We only have 2 more to do. It's up to you. We can stop now. We can go till 9:30, and I'll charge you for an hour and a half. Your choice.
I think I have a pretty decent handle on these last couple.
Okay.
But
Let's go ahead and stop. Let's go ahead and stop now then.
All right. Thank you for your help.
Yeah, you're welcome. This, I think, works a lot better when you give me problems that we can solve rather than just general principles. Don't you agree?
Yeah, I agree.
Yeah. Yeah. Because this is what it comes down to. This is what you have to do on the test.
Mm-hmm.
So, all right.
All right. Thank you very much.
You're welcome, and I will talk to you next time.
Sounds good. Bye.
Okay, Paul. Bye-bye.